FMA, work energy, and impulse momentum. All right, so kind of just give you a little roadmap of where we're headed. All right, so we're going to do FMA. We're going to do it in 3 different coordinate systems. The 3 that we just did, right? Cartesian coordinates, normal tangent, and polar coordinates. Then we're going to go on and we're going to do work energy problems. Certain problems there's going to be way easier to solve with work energy. And then impulse momentum is going to be used when there's collisions, if we ever have any collisions. There's some pretty cool stuff that comes from that. Okay, so first one we're going to do is Newton's second law of the FMA, and then we're going to do Cartesian coordinates. Okay, so let's dive into that. So Newton's second law, this is what we're calling the FMA procedure. FMA. Newton's second law is sum of the forces. The external forces, I'm going to emphasize that, external forces is equal to mass times acceleration, right? And these are vectors. Right. That's it. I mean, that's it. That's going to lead us to our acceleration equations. Once we get acceleration equations, then we go to kinematics, the geometry of motion, to solve it. Okay? These things are going to come from our free body diagram. Right? Those really got emphasized last semester, or should have. Right? And then once we get to this, once we get that, then we're going to do kinematics. Okay? Like I said, we're going to do 3 coordinate systems. Right, 3 to Cartesian, normal tangent, and polar coordinates. Oh, I always like to put a little roadmap just so there's no surprises as we go along. And just to highlight that there's a method to all this madness that we got going on. Okay, so let's talk about Cartesian coordinates. Right. Like I said, all these things are vectors, so we're going to write that equation down again. Sum of the forces, external forces, is equal to mass times acceleration. Right? In Cartesian coordinates, the external forces are going to be can be in 3 different directions. Sum of the forces in the x, in the I direction, plus sum of the forces y in the j direction, plus sum of the forces z in the k direction. And all that's equal to mass times acceleration in the x in the I, plus mass times acceleration y in the j, plus mass times acceleration z in the k. Right? When we explode, right, when we look at this in vector form, and we look at that in vector form, then it just explodes into the I, J, and the K, right? What's nice about this, right, is in Cartesian coordinates, only the J's affect the J's, only the I's affect the I's, the J's affect the J's, and the K's affect the K's, right? They're all independent of each other, and that's it. So you basically just end up with 3 force equals mass times acceleration equations, right? And the x, the y, and the z. Again, sometimes you could see it, and if you want to do it this way, go for it. Sometimes you deal with vectors like this. You can call this sum of the forces x, sum of the forces y, sum of the forces z, right? You can write it in brackets like this. You do it as mass times acceleration x, acceleration y, acceleration z. Okay. If you want to do them that way, you could do it that way. Sometimes, so if you're going to do some of these things in your calculator or with MATLAB, which is totally fine to do. These ones you don't really need those tools necessarily, but when we get into 2D rigid body stuff, we get some pretty complex vectors, and so using your calculator or using MATLAB might be helpful, but we'll get into that later. But you can write that way. That's a different way of writing vectors. For the sake of this class, I'm just going to do the IJs and Ks. Okay. But then when you write it this way, these guys these guys are equal to these guys equal to these guys equal to these guys. You guys done vectors before? You have, right? No? Yes? Yeah? Right, that's differential equations. What What would you class it as? Is that what it is? Differential equation. Yeah. Did you hate him? Or did you like him? Hate him? Like him? Nate Dogg, you hate him? You like him?
Love him.
Love him. Good. Good answer. Good. I love him too. I love him too, Nate Dogg. Okay. So I mean that's our equations of motion, right? That's what these are called. Right? EOMs. Right? And vector notation is up above there. Right? But we're going to kind of break them into the three different ones, right? There's one equation of motion. There's another equation of motion. There's another equation of motion. Okay. So when you're doing Cartesian coordinates, you get three equations of motion. Some of the forces x, y, and z. Right? Since we have particles at this point, we don't have a moment on a particle doesn't do anything. When we get into 2D rigid body stuff, we're going to have some equations of motion associated with moments as well. You're going to have a rigid body, and there's moments can act on rigid bodies where they can't really act on particles. So we'll end up with 6 equations of motion when we do 3D rigid body stuff. Okay, so I'm going to give you some rules. Again, I'm trying to really make this thing as procedural as possible, right? So we're going to draw a free body diagram, right? The forces, these forces that we're talking about, those come from the free body diagram, only from the free body diagram. So we're just going to draw a free body diagram just like you did in statics. In statics, though, you set it equal to 0. In this case, they're going to be equal to mass times acceleration in the respective directions, okay? So my rules for doing a free body diagram, a checklist, if you will. First step, isolate particle. It's pretty easy, right? In this case, it's actually usually just dots, right? Because they're particles, right? We're going to isolate that. We're going to replace supports with appropriate moments and forces, right? Replace the supports with appropriate moments and moments and forces. We're going to sketch applied loads. We use that interchangeably. Loads and forces we use interchangeably. And then the fourth step, pick a coordinate. They don't have to be done in this order necessarily. Label on diagram. We'll see that's important today. We're going to do one where it's on a ramp and we're going to kind of have a wonky coordinate system. But it's always important to put it on there so you know what's happening, right? And then we're going to label dimensions and angles on diagram. Anything that's important, any geometry that's worth, that's going to help us answer these things. Okay. So when we do this example here in a little bit, we're just going to follow these steps. Okay. Then the procedure overall for solving these problems, the procedure that we're going to use, the overall procedure, again, trying to make this thing as procedural as possible. First step when we solve these problems is we're going to do a free body diagram. Right? This is worth points. Do it. Okay? I know sometimes the problems are going to be, oh, this is easy, I don't really need a free body diagram, and you leave it out. And oftentimes it's going to it can lead to the wrong answer. But also, if you don't include it on your solution, I'm not going to give you full credit. Okay? I'm not going to do it. Right? So it's worth points. And trust me, it's worth doing it because it helps you solve the problem. Okay? Then you're going to write equations of motion. Write down EOMs. In this case, there's going to be 3 equations of motion, right? And then we're going to do kinematics as required. They haven't gone away. They haven't gone away, but they have gotten a little bit easier. Right? So I say kinematics is required. Sometimes you don't have to do much in terms of kinematics, but sometimes you do. And the fourth step is to solve it. Okay? That's it. Right? If you follow these steps each time, right, and kind of mark them in your solution, right? Because again, we're trying to make our solutions as clear as possible. If you do that as you're going through and you're really clear and concise, it helps. I mean, it really does help. It helps to follow this procedure. When students run into problems is when they go all willy-nilly, right? They're just like, I look at it and I see what's happening and I'm just gonna start throwing stuff down. And sometimes you get the right answer, but then it's also hard for me to grade. I'll get mad at you. Right? And then, or if you get the wrong answer, I can't find what went wrong, right? Just follow these steps, please, for your own sake too. Okay, everybody get that? Let's do a problem now. It's very similar to the problem we did before. The problem we did like this before, they gave us the acceleration equation. So we're going to do this one where they don't give us the acceleration equations. This is all that they're going to give you in a problem like this, right? The spring is an undeformed position when the mass is released. So it's an undeformed position, holding it. We're going to release that mass, and it's actually going to drop and then come back up, right? It's going to oscillate back and forth. But at this point, we're going to take it and we're going to release it, okay? And they give us the stiffness of the spring, 80 newtons per meter, and the mass is 1.8 kilograms. And then what they're asking for is the velocity of the mass when it hits the floor, right? So we have that drawing over there. It's going to drop 0.3 meters. It says, what's the velocity when it's going to hit the floor, right? But by the way, this problem absolutely screams work energy, okay? But we haven't learned work energy yet, so we're not going to do that. You got potential energy that you're releasing it, and it's going to go into kinetic energy and energy in the spring, potential energy in the spring, but we'll come back to that later. Say we don't know that yet, right? So let's go through those steps. So then you look at it, and you're like, what do I do? What do I do? Well, look at the procedure, right? Just go back to that procedure. It says, hey, first thing we're going to do is draw a free body diagram. So step one, F, B, D. Okay. So my free body diagram. Then I was like, okay, well, what do I do for a free body diagram? Well, I isolate my mass, right? You don't have to draw it as a box. You could draw it as a box if you want. Sometimes, right, it's just a particle. So I isolated my mass, right? Then replace all support conditions with forces. This one isn't really supported, right? But it does have an external force on it, okay? What forces do I have acted, or it has several extra forces. What forces do I have acted on this thing? Gravity, right? Somebody's got to yell that one out every time. Right? That's good. You could be my gravity guy. I'll be like, what do we do? Mass times gravity. Okay? That's the weight of the object, right? It's mass times gravity. What else? Tension. Yeah. You got the spring applied to it, right? Right? This is one of those cases where it's like, I'm going to draw it this way, right? K times X. I'm going to say that it's going up, but it actually could be going down, right? And go either direction. If the mass is going up, then the spring force would be going down, right? And there's a reason why I drew it that way. Partly, so I mean, we'll get to that in a second. So there's my mass. I've replaced all my forces, right? The next, did supports, did external forces. The other thing is coordinate system, right? We have no coordinate system. I'm going to define my coordinate system for whatever reason. Right? I could do whatever I want. I'm going to do it this way. Let's have a coordinate system. It starts at 0 there, and X is down. Why? Because I can. Because I'm a doctor. And I think that's a good way to do it. I could say X was up, but usually for whatever reason, like in structural engineering, any deflections down we call positive deflections, even though it's a downward deflection. But anyways, I'm going to say, why not Y? I don't know, because I don't want to. I like writing X's better than Y's, right? But as long as I label it on here, that's it. Okay? And so then if you're trying to figure out which direction the spring goes, you think of if it's moved in the positive X direction. So if the object is moved in the positive X direction, which way does the spring move? In that case, it would go to up, right? I'd pull it down, the spring would apply the force up, right? If I would have defined X as being positive up, then I would say, I'm going to move the object up, and my spring would go down. And then the signs work out if you do it that way. Okay, so just again, that's one of those little steps that I was mentioned earlier. There's a reason for it. There's a reason why I drew it up. And that's a rule that I stuck to. The rule is, if I move it in the positive direction, which way does the spring act? Then you draw it that direction, okay? Okay, that's it, right? I mean, those are our forces. That's the only forces we have acting on that particle. Isolated particle, put our forces in, put our X in there, okay? Step 2, equations of motion. UMs. Okay. You only have one, because we only have motion in one direction, right? Technically, there's the other directions. There's the z direction and then the y direction, but it's only moving in one direction, so I only have one equation of motion. So my equation of motion, sum of the forces in the x is equal to MAX. Right? And then what do? I just look, at this point, I look at my free body diagram and say, what forces are acting in the x direction? Well, I got mg acting in the positive direction. Why is it positive? Because it's acting in the direction of positive x, right? And then my kx is acting in the negative direction because it's acting in the opposite direction of the positive direction of x. So that's what we just write down. We say mg, positive mg, minus kx is equal to MAX. Okay? And at this point, I need, again, we're getting ready for some kinematics. I need AX. I need the acceleration as a function of something. And so at this point, I just divide both sides by mass, right? And I get, there's my acceleration equation. AX is equal to G minus K over M times X. I don't know why I'm boxing it, but that's just, maybe it's just because it's important. So that's my acceleration equation, right? Then if you looked back, I don't know, a week or so, we did a problem with a spring, and if you look back at the equation of acceleration that we gave you, it was in this form, right? It was in form. It was like AX is 32.2 minus 50 times x, I think, is the equation from a couple weeks ago. That's what it is. 32.2 was gravity in that equation, right? And so that was a real equation that you used. Right, so at this point right here, right, we're not done yet. What it's asking for is the velocity when the mass hits the floor. Well, what kind of problem is this? So now we got to do kinematics. This is kinematics. 3 is kinematics. What kind of problem is this? Yep, acceleration, a function of position. Oh no, what am I doing? Kinematics. Right, through kinematics, and that's exactly right. This is acceleration, a function of position. We have a method for solving these things. Okay. This is what I lied to you earlier, and I said we were done doing integrals. We're not. We just have a little bit more. Uh-oh. Right. And you can look back. If you looked back at your notes, you could find how we solve these problems. Right. You can't just integrate with respect to time because the acceleration is not a function of time. It's a function of position. Right. So AX. If you looked back, we did this. AX is dv dt. Use the chain rule. dv dx dx dt. dx dt is just the velocity. So we got v times dv dx, and then you isolate all of the x's and the v's. So we got g minus k over m dx is equal to v dv. Right, I just substituted in what ax was. Right, this is just ax. Right, I just put in ax there into that, and this is an x here. Right, and I integrate and integrate. Right, this is an integral of dx, right? So this is going from 0 to 0.3, and this is going from 0 to VF. And that's what we're after, is what that VF is up there. And so I just put in my definite parts. Do you have to put the definite parts in here? No, you could solve those integrals as indefinite integrals and then apply boundary conditions and then figure out what the constants were and then come back and put the time in there. Did I do something wrong? Yeah, I wasn't done yet. That's it, you figured. That x visit is right there. I was just going to say, what did I do wrong in that equation? Right? Thank you. Is that the same question over here? Yeah. You gotta keep on. I do it on purpose. I do it on purpose to keep you on your toes. Yeah. Not to confuse you at all. Okay. Cool. So at this point, you just carry out those. You carry out those definite integrals, and then what would pop out is VF, right? And so in this case, VF would be equal to 1.37 meters per second. Right? And you're studying for the exams and stuff like that. It's not a bad idea to go back and just just make sure you could do that. I just do it in my calculator, so make sure you could do this stuff either using math in your head, right, or using your calculator how to do these integrals, because those would be fair game, right? Or any of the math really, right? And so then step 4 was actually solving, which is kind of mixed in with what we just did right there. Sometimes it's not a really definite break between the problems. It was solving those integrals. Okay? And that's the other reason I like it too, is just like the solutions are just so pretty, right? It's just really clear. It's just free body diagram, equations of motion, kinematics, and it's solved. And every one of them follows the same pattern. Every one of them. They just get more complicated. Let's do a more complicated one. Let's do the next one here. This sucker right here. By the way, if I'm going too fast and you need to see a page or something for it, you can tell me. It's okay. I mean, I might shame you for writing slow, but I won't judge. I won't judge you. I mean, I will, but it won't hurt your grade at all. Okay. All right. So now we got this thing. And I mentioned this last time. There's a little block sitting on a ramp. Right? Block sitting on a ramp, and it's a frictionless surface on that ramp, and I've got a cord P that's attached to that. I'm gonna pull down on this P, right? So I'm gonna yank down on this P. You can imagine if I pull hard enough on that P, this block's gonna move up, right? If I don't pull on it at all, that block is gonna slide down, right? And so what we're asked to find is the P required for it to move up the surface at 2 meters per second squared, or move down at 2 meters per second squared, what P would be required. Because it would want us, in this particular case, it would want to go faster than 2 meters per second down if I didn't hold on to that P. It would slide faster than that down there. Okay, but I'm going to hold on to that. And you might be like, oh my God, what do I do? Right? This is more complicated. There's a lot of shit going on, right? What do I do? Who cares, right? Just go back to that procedure and follow that freaking procedure, right? It's gonna lead us there, right? So I know just trying to rely. I mean, obviously look at it and try to apply some intuition, be like, okay, what's happening? Like what we just talked about, like, oh, it's gonna slide up, or it's gonna slide down, if I pull the thing. Sure, do that. But then when it comes to solving it, boom, just go right back to that procedure. Free body diagram, equations of motion, kinematics, it's solved, right? And it'll lead you there every time. That's what's beautiful about this part. Okay, step 1, free body diagram. FBD, right? Isolate our object. A lot more going on in this one, right? Isolate my object. Give myself a little bit of room here, right? There's my object, isolated. Uh-oh. Okay. All right, what do I got for forces acting on this? You're the gravity guy. You're the gravity. That's right. That's right. Mass times gravity. Right? What else? P? Yep, P's acting on that. Okay? I got P going down like this. I also have P going up like this too. Right. I got both of them, right? Because there's tension in that cord. It's attached to that point. So you got it down, and it's going to be up and to the right too. It's constant through that in tension there, and so there's going to be P acting up and to the right too. Okay. What else?
Normal force.
Normal force, right? You got a normal force. I mean, it doesn't have to be. You could draw it. The way I drew it there, a little off. Oh, I don't want to curve. Normal force. What did I do? What did I do something? We tried to solve the last one. Do this one?
The last one.
Okay, all right. That should be all of them, right? Right? We got, right? And I kind of did it out over there. Like, I guess I said, I think that one of the steps, that's what I call it a checklist. But replace the supports and reactions with equivalent forces. So replacing the reaction and my angle's off. My angle off. Yeah, that's not too bad. So then, and then I replaced that normal forces coming from that. I got mass times gravity going down. I got P going down. I got P going up to the right. That should be everything, right? And then I wouldn't leave it here, right? Because I said the next step is we need to label coordinate systems. Kids are home. Do I answer this? I'm not gonna answer. Okay. Mass times gravity down, P going down, P going up to the right. Normal force doing that. Okay. I need to put coordinate systems, right? I freaking hate ramps because it's like, do I tilt my axes? Do I leave my axes the same? Right? I don't know. I don't know if there's any real steadfast rule. You could do it either way. No matter what, you could do it either way. I could tilt my axes and get an answer, or I could leave my axes just being normal and I get the answer. Right? Either one works. Just one way is slightly easier than the other way. Right? And in particular, they're telling us what the accelerations are up and down the ramp, right? This way and this way. And so if I were to do that have my coordinate system, straight like this, then my accelerations would have an X component and a Y component. And so it gets a little messy. So I'm gonna tilt my axes, right? I'm gonna line my axes up in the X direction and the Y direction. All right, sorry, in the X and Y are gonna be kind of tilted to the side like that, right? And you can do whatever you want with your coordinate system, right? So I'm gonna call X this way, right? And Y this way. Okay, I'm gonna text my son. It's an emergency. Okay. And you could do that. And again, it just makes the problem slightly easier when we do that. Okay. And then the next one is putting any dimensions and stuff in there. There's lots of dimensions and angles and stuff that we have to label in here. Okay. So let's do that. Right. Here's an angle that's going to be play in. This is going to be 20 degrees here. This is given to us in the problem statement. Right. And eventually, I'm going to move this here. Eventually, I'm going to have to break this into the mass times gravity. I'm going to have to get that into both the X and Y direction, right? So, right, I got to figure out what component's going like this, what component's going like this. Right? I mean, because when I sum the forces in the X and the Y, mg is now acting in two directions. If you put your axes straight up and down, it makes this part easier, right? Because mass times gravity is in the Y direction, and P is going to be acting in the Y direction. So, but again, you can always get to the same answer as long as you're careful. Again, it's just slightly easier here. So in this case, I'm going to have to break mg into two different components, right? And then I'm going to have to break P into two different components down here as well, right? One that lines up with the Y direction, and then one that lines up in the X direction. Okay? And it's important to label the angles in that as well, right? This will end up being the 20 degrees here, and this is the 20 degrees here. And there's a bunch of different ways to kind of envision how that ends up being 20, right? If you draw little diagrams and use your geometry skills that you've developed over the years, right? And what that ends up being. Cool. So that is our free body diagram, right? A little more involved here, right? But if you do it this way and you keep it clean like this and you use a straight edge, I do. I recommend you start use a straight edge on your homeworks, and then it helps you have a clear mind. Just it's clear and concise, and it's easy to understand what's happening, right? You see, right? I have terrible handwriting. Look how freaking clean that is, right? It's really clean. It's really easy to understand what the hell's happening with that. Okay? Free body diagram. Done. Okay? So let's go now to equations of motion. Right? We drew that, and we write out our equations of motion. Right? And we have some of the forces. It's only a 2D problem, so we're just only going to have some of the forces in the x and the y direction. Some of the forces in the x. Some of the forces in the x. At this point, what I do is I just look up at my free body diagram and I say, what forces are acting in the x direction, right? And let's highlight them here, right? I have P acting in the x direction. I've got mass times gravity, a little component of the mass times gravity, and a little bit of this P acting back that direction, right? That's it, right? And so at this point, I just write down those 3 forces in the x direction, okay? And only the ones that come off of that free body diagram. So what do I have acting on there? Well, I've got, and then positive or negative, right? This one's going to be positive because it's acting in the positive x direction. This is negative, acting in the negative x direction. That one's negative, acting in the negative x direction. So then reflect that in your diagram or in your equation of motion down here. P minus mg sine 20 minus P times sine 20 equal to mass times acceleration in the x direction. There's our equation of motion. Literally just look at your free body diagram, which we spent some time on, and we made it look nice and pretty. We labeled the different components, and this just pops right out. There's just a little bit of geometry to get to mg sine 20, right? A little trigonometry. My sons the other day, or a couple of years ago, when we were studying math together, they're like, why do I need to know sines and cosines and Pythagoras? Whoever does that? I was like, oh, I do that every day, right? I do it every day. I break that thing down like that. So I have one kid. I do a lot of math tutoring with my kids. And if you may recall doing that with one of your parents, it is not a pleasant experience. One of us ends up crying every time, right? It's either me, because I'm so frustrated that the kid doesn't get it, or it's him, because I've yelled at him until and ridiculed him. I swear, and my wife has to intervene sometimes. She comes over, you two need to separate, right? It is intense. I used to study with my dad back in the day. He was an engineer, and it absolutely is not pleasant in any way, and that's how it's supposed to be, right? Right. Anyways, I got one in pre-calc and one in geometry this semester, so we'll see how that goes. We'll see how it goes. I'll share some stories if there's any fights happening. All right, some of the forces in the y. Now what I do is I come up and I look to see what's acting in the y direction. Well, I got a positive n right here. I've got this component of mass times gravity, and I got this component of p. Right? So it's just those 3 forces right there. And that's literally like don't think of these, again, don't think of this inertial force as being a force, right? I just literally look at my free body diagram and I write those things down, right? The P and the mg are going to be acting in the negative y direction, and then the n is acting in the positive y direction. So I just come down and I just write those out. Normal force minus mg cosine 20 minus P cosine 20 is equal to MAY. Okay, not quite there. You're like, oh my God, what's happening? Okay, so the next step is kinematics. The kinematics in this one are kind of, they're not really like, there's no integrals involved. It's just what is happening with the motion, right? And again, it's just this. That's why I say kinematics as required. That's why the statement says that, is because it's just, we don't have a lot going on here. It's just what's happening with the geometry of motion, right? What do we know about a couple of these accelerations over here? Just think about what's happening. This acceleration x and acceleration y. What do we know about these guys? Yeah.
Well, so don't you want to do like two equations of each, one with the positive ax up the current, or one with
Absolutely. That's right. That's exactly right. There's two different problems we're solving here, right? One is it's accelerating up at 2 meters per second, and this is from the problem statement. The other is it's going down 2 meters per second. So that's here, right? That's the acceleration in the x. So it's exactly right. I'm gonna have one going up and one going down. What about, that's great. We'll get to that in a second. What about the y? What's happening in the y direction? Zero, right? It's not accelerating in the y direction. So this just goes, this over here is equal to 0. Right, which is just statics. Right, what I would use that for, would be to determine what the normal force is, right? They don't tell us what the normal force is. There are two unknowns in this, right? The normal force, and I'm solving for the P required for it to go up and down. So I don't know P, I don't know N, but if I asked you what's the normal force, or if this was a function of, if there was friction, if I said there was a friction there, right, there'd be another force. We didn't draw it on here, but if I did right now, this is frictionless surface. If there was friction, there would be a friction component acting back like that would show up in this equation right here, and it would be a function of the normal force, which would be showing up in this equation down here. And it gets a little more complicated, but definitely solvable. Okay, but so in this case, it's equal to 0. I don't really need that right now. I don't need the second one, the second equation down at the bottom, because the only thing I'm after is this P. And if you look up here, right, I'm gonna know what AX is. I know what MG is, right? The only unknown in that equation would be P, and I could solve for P. I could set that equal to 2 meters per second, and it'll give me a P, and then that's what I need. That's what one of the problem statements says that I need. Okay, so that's great. Good job. All right, so then this say, I just want to always put them down. 3 kinematics, just to make it clear, right, is that AX is equal to 2 meters per second squared, or negative 2 meters per second squared, and AY is equal to 0. I would say that would be my kinematics, just the geometry of what's happening. Okay, and then for solving, okay, in that case, we'd have two cases as was mentioned, right? One, we do P minus mg sine 20 minus P sine 20 is equal to mass times 2. Right, and we have all those values except for P. P is the only unknown in this. Right, I'm just after that. What do you do at this point? Calculator. Right, and this would be P is equal to 1.63 newtons up. That was one of the questions, was how to, so if I pull down on that cord at 1.63 newtons, it's gonna move up at 2 meters per second squared. It's gonna have an acceleration up at 2 meters per second squared. The second part, I'm gonna cheat because I have a tablet and they're awesome. I'm gonna copy that thing down there. I don't know if this saved any time in any way, but I did it anyway. 2, and then over here, instead of being equal to 2, you set that equal to negative 2. Because it's going to be negative 2 meters per second squared. Okay, and you solve that same equation. Plug that sucker into your calculator, and then you get P is equal to 0.412 newtons down. So if I pulled 1.63, it's going to go up 2 meters per second squared. If I pull on it, kind of just slowly letting it down, then if I pull on that with 0.412 newtons, it will go down at 2 meters per second squared. If I didn't pull on it at all, it would go faster. Right? And like I said, if totally solvable, just a little bit more complicated, if I said that there was friction. If I said that there would be friction, you would just pick up an extra friction force, which would be equal to the normal force. The friction force would be equal to the normal force times mu, right? And so then you would end up with, you would have a friction force in the x direction, and then you'd have the normal force down here. And the stuff down, the friction force would be a function of what's happening in the y direction. And so you'd have two linked equations that you would have to solve, two equations and two unknowns that you would have to solve for, which again, with math, super easy. Okay, any questions about that one? See, this procedure's beautiful. Just leads us to the exact answer every time. Okay, that's Cartesian coordinates, right? Nice and clean, x, y, and z direction, right? But again, there's gonna be certain times that this coordinate system isn't gonna be very helpful, right? And we need to use a different coordinate system. The different coordinate system we can use is normal tangent coordinate system or polar coordinates. We'll talk about normal tangent first. Normal tangent doesn't get used that much, but we do use it to help derive a bunch of equations and stuff in 3D rigid body stuff or 2D rigid body stuff. So I keep it in here for that. But really, if something's traveling in a circle, you can use polar coordinates or normal tangent. They're exactly the same with the exception of one positive or negative sign on the centripetal acceleration. Okay, but I mean, it's still same procedure applies, just a little bit more, just a little bit different in what vectors we're talking about. Okay, so this would be like if you had a ball on a string and you're whipping around in a circle and it said, what's the tension force in that string when it's traveling a certain omega? That's where this stuff would play in, right? Okay, you couldn't do that with Cartesian coordinates. All right, so again, just a refresher, if this thing's traveling along the path, you'd have one of your coordinates doing that, which is the ET direction. And then we would have perpendicular to that, pointed back at the instantaneous center of curvature, an EN direction, a tangent and a normal direction to our coordinate system. In this coordinate system, when we talked about velocities, this is where our velocities were. Right? The velocity vector is v in the ET direction. Right? It's always in the ET direction. The velocity is always tangent to the path. Right? And so velocity is just in the ET direction. The accelerations, which we need because we're gonna sum the forces and they're equal to the accelerations in these two different directions. We have the acceleration is AT in the ET direction and AN in the EN direction. AT in the ET was just the derivative of the velocity. It's your change in speed. Your AT is just your change in speed, your acceleration along the tangent path. Okay? And then our normal is our centripetal acceleration, right? Our normal acceleration is that. It could either be written as v squared over rho, or it could be written as rho omega squared. Okay? Those are the two different forms you usually see it in. Right? It all depends on if you have velocities or omegas. Okay? So when you do this, you just literally do the same process that we had before. You do your free body diagram, you write your equations of motion, go from there. And then, I mean, I'll just flash down to this, run out of time here, but our equations of motion, right, it's just, again, you write out the vectors, you have the ET and the EN direction, but what you end up with is just, I sum the forces in the ET direction, and that's equal to mass times acceleration in the ET direction. Simple as that, which is just acceleration, just your change in speed, right? Your change in velocity, right? And then you do the same thing in the other direction. You sum the forces in the N direction, and then it's equal to mass times acceleration in that direction. And it just so happens that the mass times acceleration takes one of those forms. The acceleration, rather, takes one of the forms. It's either v squared over rho, or it's m rho omega squared, just depending on which coordinate system you're using, right? So everything stays the same as we just did in Cartesian coordinates. It's just when we set it equal to mass times acceleration, those accelerations in those different directions are slightly different, right? It's going to be like, just my acceleration in the N direction is going to be a function of the velocity along the tangent, right? So it just gets a little more commingled, a little more difficult. Okay, and so that's what we're going to do next time. Is we're going to figure out, we're going to do a problem where something's traveling in a circle, and we're going to figure out what the minimum speed is to launch off of this so we actually catch some air. And then we'll do another one where somebody sets up a rope swing, and these guys jump off the rope swing, and they go whipping down there, and it's asking what's the tension force in that. And we'll solve both of those problems. Then we'll go on to polar coordinates, and that's it. Okay. This stuff that I'm covering today is on next week's homework. Cool. All right. Great. Have a good Wednesday. It's not smoky today. It was gross yesterday.